So this will be the fifth lecture over NMR spectroscopy. So on this one we'll look at coupling constants in a little bit more detail, and we'll look at how that affects the NMR of molecules. So if you have two hydrogens on adjacent carbons, such as here, so they're vicinal hydrogens, then they have coupling constants of about 7 Hertz. And this is all greatly impacted by how much, if you have free rotation around bonds or not. Okay, so if you have hydrogens on a cis alkene, so those two hydrogens cis to each other, their coupling constants about 7 and 12 Hertz, so on average of about 10 Hertz. If the two hydrogens on an alkene are trans to each other, then on average about 16 Hertz coupling constant, so that's pretty large, one of the larger coupling constants. So hydrogens on the same carbon of a double bond, so those are geminal, and in this case they're not equivalent because A is not the same as B, right? So A is cis, or this hydrogen is cis to A, whereas this hydrogen is cis to a B, so those two hydrogens are different, so they can split each other, and those coupling constants are about 2 Hertz. Hydrogens on a benzene ring, so obviously these are neighbors, so they would split each other, so ortho coupling is about 8 Hertz. So this is what's a little bit different than what we've covered so far. So these two hydrogens are not neighbors of each other because they're not on adjacent carbons, but they can still couple with each other. So that's what's called metacoupling, so that's about 2 Hertz. Or hydrogens on a benzene ring trans to each other can even couple with each other, but those coupling constants are about 1 Hertz. So whether or not you would see those couplings, whether they would split each other or not, and whether you'd be able to observe it since the coupling constants are so small, would depend on your instrument. If you have a powerful magnet, and you have really good, so you have better resolution and you have really good shim, then yeah, you can see coupling constants that small. But if your instrument is not as powerful and you don't have very good shims, then you're not going to see those couplings. Okay, allylic coupling's pretty significant Hertz. So if you have a hydrogen on an alkene and the adjacent position is the allylic position, so that's allylic coupling. Or so in this case with an aldehyde at the adjacent position, or in this case just hydrogens on an alkyl chain at the allylic position, so those coupling constants are about 6 Hertz. Or if you have hydrogens on the same carbon, there are situations where those two hydrogens are not the same, and we'll look at lots of examples of that in the next lecture when you have chirality involved. So if two hydrogens on the same carbon are not the same, then they can split each other, and they have relatively large coupling constants of about 12 to 15 Hertz. Okay, so let's take an actual example and apply this, and let's see how that affects the NMR of molecules. So if we took the NMR of this molecule, so the benzene ring it's independent of the alkene because they're not neighbors of each other, so they shouldn't split with each other. So we'll just focus on hydrogen A, B, and C. They're all neighbors of each other, so they can all split each other, but the simple n+1 rule does not work in a molecule like this because of the restricted rotation around the double bond and the big difference in coupling constants between cis coupling, trans coupling, and geminal coupling, right? Where the trans coupling is 16 Hertz, the cis coupling is 12 Hertz, and the geminal coupling is 2 Hertz. So then we have to use what's known as a modified n+1 rule. So if we just focus on HC, for example, so HC is going to be split by HA, that's one neighbor, so that's a doublet. But then HB is going to come in and split each of those peaks. So then HB is a neighbor, so one neighbor, 2 peaks. So each of those peaks from HA splitting is then going to be split by HB into doublets. So you end up with a doublet of doublets for the NMR. So this is useful to look at using what's called a splitting tree diagram. Makes it a lot easier to see what kind of signal you would expect for a particular hydrogen. So if we take HC, for example, so HC has HA as a neighbor, and you always do the biggest coupling first. So HC is going to be split by HA, so by 16 Hertz. So we'll take HC signal and split it into a doublet. So C is then split into a doublet by HA, and the difference between those two peaks is 16 hertz. But then you have HB is then going to split each of those signals into a doublet. So then you end up with 4 peaks. And so HC to B then is cis coupling, and that's worth 12 hertz. So we're going to go from here, and then we're going to go over 6 hertz and that way. So that would be 6 hertz. And then we're going to go over 6 hertz this way as well for that doublet. And then the other lag is going to be split as well. So we would go over 6 hertz this way and 6 hertz that way. And then that would be your 12 hertz coupling constant. So you actually end up with 4 peaks then. So they would look like this. Or of course on the NMR, it would look a lot closer together, those signals would be. But the point is the distance between these 2 peaks and those 2 peaks is 12 hertz. So what's the distance between these 2 peaks? Well, we can figure that out from the splitting tree diagram. So if we just drop a vertical from here, so we went over 8 hertz to get to this point. And then when this signal got split, we came back 6 hertz this way. So there's 2 hertz here. And same for here. We went over 8 hertz this way, and then you come back 6 hertz this way. So there's 2 hertz there. So the difference between these 2 signals would be 4 hertz. Right, so your coupling constants here would be J1 is equal to J3 is equal to 12 hertz, and then the signal in between, the peak in between, is J2, right? So this is J1, this is J2, this is J3, and so J2 would be 4 hertz. Okay, so 4 peaks. So how do you know this is not a quartet? And that's because quartets look like this. Quartets are in a 1 to 3 to 3 to 1 ratio, and then furthermore for a quartet, J1 equals J2 equals J3, and that's not what's observed here. So this is in a 1 to 1 to 1 to 1 ratio, and J1 equals J2 or 3, but does not equal J2, right? So it's not a quartet, it's a doublet of doublets. Okay, so we could do the same thing for HA and HB. So what does the signal for HA look like? So HA is going to be split by HC, 16 hertz. So you do the biggest one first. And then, so that gives you a doublet, right? That would be these 2 peaks, so that's a doublet. And then HA is also split by HB, but that's only 2 hertz coupling. So you're going to go over 1 hertz this way, and you would go over 1 hertz that way, right? And the same on the other leg of that doublet. So you end up in with a doublet of doublets as well. Another doublet of doublets, but the distance between those peaks is different because of the coupling constants are different. So so this is 2 hertz, this is 2 hertz. How many hertz between those 2 peaks? Well, so let's again drop a diagonal or drop a vertical down here. So we went over 8 hertz to get to there, and then we came back 1 hertz. So this is 7. And the same thing here, we went over 8, we came back 1, so this is 7, so that's 14 hertz in between those 2 peaks. And if we do the same thing for HB, so HB is split by HC, and that's cis coupling, so that's only 12 hertz. And then each of those peaks would be split by HA, geminal coupling, which is 2 hertz. So we get 2 hertz there, 2 hertz there, and then how much in between? So we went over 6, and then we came back 1, so this is 5. Right, 1 over 6, came back 1, so this is 5. So that would be 10 hertz in between there, right? So HA, HB, and HC would all be doublet of doublets. Okay, so then how can we so this would be what the proton NMR of that molecule would basically look like. So around 7.2 ppm. So somewhere between 7 and 8 ppm would be your benzene ring. And even though those two hydrogens are the same, those two are the same, and that one's unique, there's 3 different hydrogens in benzene. The chemical shift difference is probably so small that they would all just overlap each other. And then you have HA and HB and HC, and they're all doublet of doublets. So how can you distinguish between which is which? You would use the coupling constants, right? So this is a 2 to 10 to 2. This is 2 to 14 to 2. And this is 14 to 12 to 4 to 12. So then if you know what coupling constants are, for trans, cis, and geminal coupling, and just splitting tree diagram, right, you can use the coupling constants to figure out which signal comes from which hydrogen. Okay, let's take another example. So we'll use 2 or 3 more examples to illustrate the use of these splitting tree diagrams and how they can be used to figure out what your spectra is going to look like. So if we took this molecule and if we just focused on HB, so it's got a neighbor there and it's got a neighbor there, so 2 neighbors. If the simple n+1 rule worked, it would be a triplet. And in this case, of course, HA is equal to HC, right? They're equivalent because of the symmetry of the molecule. So the coupling constant between HA and HB is the same as the coupling constant between HC and HB. So, of course, HB should be a triplet, right? So this coupling constant is about 6 hertz. So if we looked at a splitting tree diagram, so let's just say HB couples with HA first. So that's 6 hertz, right? So we go over this way 3 hertz, we go over that way 3 hertz. And then for this legs of the splitting tree diagram, so this was originally a doublet because it was split by HA, and now each of those peaks is going to be split by HC into a doublet. So you would end up with a doublet of doublets, right? But in this case, you don't. You end up with a triplet. And why? Because this coupling constant is 6 hertz. So you're going to come back 3 hertz this way, and you're going to come back 3 hertz that way, and those 2 inner peaks are going to meet in the middle. So you only see 3 different peaks. So triplet, right? And you see a triplet in a 1 to 2 to 1 ratio, which the splitting tree diagram helps understand that as well, right? Because here you have 2 lines converging, and here you only have 1 and 1. So the splitting tree diagram helps predict what the relative ratio or intensity of those peaks should look like as well. So because the coupling constants are the same, then those 2 inner peaks merge, and you only get 1 peak instead of 2 doublet of doublets. You get a triplet, right? And then of course the triplet. So in this case, J1 would equal J2, 6 hertz, and you would see a 1 to 2 to 1 ratio for the signals. Okay, so if we take this molecule as another example, so again, let's just focus on HB. So it's got 3 neighbors here and 2 neighbors there, so 5 neighbors. So it would be 6 peaks if the simple n+1 rule worked. But in this case, it's a little bit more complex than that because the coupling constant between A and B is 6.8 hertz, but between B and C is 7.3 hertz, so not a big difference, only 0.5 hertz difference, but it is different, which means if your NMR was powerful enough magnet so that you get really good resolution and really good shimming, then you can see you're not going to get a sextet here. You're going to get a more complex spectra than that because the coupling constants are different. Okay, so if it was a sextet, you would get a 1 to 2 to 3 to 3 to 2 to 1 ratio. Okay, so you're going to do the biggest coupling first. So blue. So the blue lines represent HC. There's 3 of them, plus 1, 4 peaks, so quartet. So HC would split HB into a quartet, so we have 4 lines coming off. And then we do the smaller coupling, so B and A is only 6.8 hertz. So now A is split, not that. So then we want to, so let's get rid of that. So then what this represents in black is that the 4 peaks from HC splitting so the 4 peaks from HC splitting, the quartet, is now split by HA. So there's 2 HAs plus 1 equals triplet. So each of those 4 legs, each of those 4 peaks from the HB will be split into a triplet. So then your splitting tree diagram would end up like this. So now you have 12 different peaks instead of 6. So it's a pretty complex spectra, right? For that one signal for the HBs. So what if the coupling constant between HB and C and B and A was the same? So if they were all 7.3 hertz, well then what would happen to this diagram? So if this splitting was a little bit larger, then you would move that peak over just a little bit, right? And if you move this over just a little bit that way and this a little bit over that way, because if the coupling constant was bigger, if it was 7.3 hertz, then you can see that those 3 lines would converge into 1, right? These 2 would converge into 1. If we move that over just a little bit and that over just a little bit, those 3 signals would converge into 1. And if we move that over just a little bit, if it was a little bit bigger coupling constant, those would converge into 1. And then we would see a 1 to 2 to 3 to 3 to 2 to 1 ratio, which would be if the coupling constants between B and A and B and C were the same, then you would just get a sextet. Okay, so if we take another example, so if we took this molecule, so HB is easy. So HB only has one neighbor, HA, so HB would simply be a doublet. So nothing complex about it, but HA is more complex than that, because HA is going to be split by HB, that's transcoupling, that's 16 hertz. And then it's going to be split by the CH2, but that's a Lillet coupling, and that's only worth about 6 hertz. So now you're not, so even though HA has 1, 2, 3 neighbors, right, HA is not a quartet. Right, because the simple n+1 rule doesn't work for HA. So we need to use a splitting tree diagram to see what HA would look like instead. So HA is going to be split by HB first because that's the biggest coupling constant, so 16 hertz. And then HB, each of those signals, so that doublet then is going to be, each of those is going to be split by HB, so there's 2 by the CH2. So 2 plus 1 would equal triplet. So each of these legs from splitting with HB would then be split into a triplet, so you would get a doublet of triplets, right, for this NMR. And so what's the coupling constants? Well, this is, so 6 hertz and 6 hertz and 6 hertz and 6 hertz on the ones on the outside, but how about the 2 peaks in the middle? What's the coupling constant between here? So if we drop this down, so again, we went over 8 hertz this way, and then we came back 6, so that's 2. We went over 8 that way, came back 6, so that's 2, so this would be 4 hertz. Right? Okay. And so these would be in a, so my triplet's not, the double of triplets is not drawn quite right? It should be, each of those should be the same height. So you know it's not a sextet because a sextet's in a 1 to 2 to 3 to 3 to 2 to 1 ratio, and you also know it's not a sextet because if it was this, then J1 equals J2 equals J3 equals J4 equals J5, which is not true here. Here J1 equals J2, and which equals J4 and J5, but it does not equal J3, right? So that's a doublet of triplets. Okay, so one last thing to talk about in this lecture. So usually in proton NMR, you get what is known as 3-bond coupling. So if we looked at these CH3s, for example, so the bond to carbon is so the bond to carbon is 1, and then the next bond to the next carbon is 2, and then these hydrogens would be 3 bonds away. So those are neighbors. So those would split the CH3, and you would have 2 neighbors, and it would be a triplet. But sometimes you can see 4-bond coupling, so that's what's called. So sometimes you can observe 4-bond coupling. That's what's called long-range coupling. So from this hydrogen, if you go 1, 2, 3, 4 bonds, so that hydrogen is 4 bonds away. So it's close enough in space to split that alkyne hydrogen. So if you just did the simple N+1, then you would say that this would be a singlet, because on carbon number 3 there is no hydrogen. That's the adjacent carbon, and so to be 3 bonds away there would have to be a hydrogen there. But if in some cases you can see 4-bond coupling, so now you have a neighbor, so that would be a doublet. So you would predict that hydrogen to be a doublet, and then the same would be true for this. If H1 can see that hydrogen on the carbon labeled 4, then that hydrogen can also see the alkyne hydrogen. Right, it works both ways. If one splits with the other, then the other splits with the one. So they would both, well, so H1 would be doublet, but then this would be 3 neighbors there. Quartet, which would be a bigger coupling constant. And then that H1 would come in and split that quartet, each of those 4 peaks, into doublets. So you would have 8 peaks there, right? But will you observe that where the coupling constants are small? So you're not going to see a doublet for 8. So you're not going to see typically this. You would typically see so there's 2 peaks there, so technically it's a doublet, but the coupling constant is really small because of the 4-bond coupling is a small coupling constant. And so then again, if your instrument, if you have poor shims or you have poor resolution, then those 2 peaks will just converge into one, and they will look like a singlet. Right? But if your shims are really good and you had a powerful enough magnet that you could get really good resolution, then you could see. And of course, the bigger the magnet is, the bigger the coupling constant would become. Okay, so we will stop there.